All right, so welcome everyone to the first seminar of the semester, the fall 2021 semester. It's my pleasure to introduce Adélie Garin from EPFL. So Adélie is a final year, I forget which year that is, grad student with Hess, and will be on the job market this year as well. So feel free to take it away, Adélie.
Thank you very much for the invitation, Justin. So yeah, the project I'm going to talk about today is actually a collaboration with Justin and other people at Albany. So Jordan and Brandon, that most of you may know, two people at EPFL, so Lida Kanari and Hess, and someone at ETH, Benjamin here. So I'm going to talk about from trees to barcodes and back again, some combinatorial and probabilistic perspective on the space of trees and barcodes. And as Justin said, feel free to interrupt me if something's not clear at any time. So the motivation for this work originally, when it started, so it started first with Catherine and Lida, and Lida was interested in neuron morphology and how to classify neurons, understand how neurons can be different from random trees, and also generate artificial neurons, which I'm going to talk about at some point today. The further motivation is about distributions of trees and also the inverse problems. So if we have the space of trees and specific distributions, for instance, neurons, but any type of trees that have similar properties, we can project that down to the space of barcodes, and you end up with a specific distribution of barcodes. And one of the questions is, if we go back, do we end up in the same distribution? Do we get something else? And all the study of the inverse problem. So the outline for today, I'm first going to recall the definitions of trees and barcodes so that we're all on the same page, similarly to how to compute persistent homology for a tree. I'm going to explain how we can use the symmetric group to classify barcodes, and then quickly go into the stochastic inverse, as I say, to generate artificial neurons. It's called the TNS. Then I'm going to talk about how many trees have the same barcode and how we can use the symmetric group as a statistical tool to study trees and barcodes. And lastly, I'm going to give some combinatorial perspectives on the space of barcodes. And so the symmetric group description here, we can actually go further, and that will give us new coordinates on the space of barcodes. So just so we have the same definitions for trees, what I will call a combinatorial tree is just an acyclic finite binary graph with a distinguished vertex called the root, because we're talking about trees, we need a root. So basically, these two trees are the same as combinatorial trees because their adjacency matrices are the same. So whether the blue, red, and purple branches, they're all attached to the white one. So the order here doesn't matter. It's just the adjacencies that is recorded. What a merge tree, on the other hand, is a combinatorial tree with a height function that we add on the vertices. And we want this function to respect the hop distance to the roots, meaning like a parent cannot be later than the child or the other way around. So we have this function, basically that could be a real height function from Morse theory. It could be the distance to the Euclidean distance of the vertices to the roots if we embed a tree in R3 and so on. The leaves are the vertices of degree 1. Branching points or bifurcation, I might also call them internal nodes, are vertices of degree 3. The trunk is the main branch where everything is attached. The root is the root. And a small remark, merge trees, they inherit a labeling on the leaves coming from this height function. So we have the first vertex, which has the smallest value for f, is 0, then 1, 2, 3. And the trunk is always going to have label 0, and we'll see why later. A barcode, I mean, most of you, I mean, probably everyone knows what a barcode is, but here, because we're more interested in the combinatorial aspect, we're just going to consider it as a finite multiset of pairs bi, di, so they're not intervals anymore, but they represent the intervals. It starts as 0 for the same reason as before for the 0 label. And a barcode is called strict if there is a largest branch B0, D0 that contains all the other, that will be the trunk. And if the birth times and death times are all different. And without loss of generality, for this part, we're going to order the bars by birth time. So typically, this is a perfect example of a strict barcode. So you probably all know about persistent homology, but in the case of trees, it can be made into a much simpler algorithmic view, which in the case of neurons is called the topological morphology descriptor, TMD. And it takes a tree and it returns a strict barcode. So technically not necessarily a strict barcode, but for the case of neuron, it does, because neurons will, in nature, you will never have two values, exactly the same, twice exactly the same value. So it can be done combinatorially speaking by using the elder rule. Basically, when two branches merge into each other, you keep the one that was born the earliest. So with the blue and the green one, the blue is born before because it has a lower value of F. So the blue continues and the green one merges into the blue one. I think that's clear for everyone, I hope. So the white one here is the main branch or the trunk, as I was talking earlier, and it's going to be labeled by B0, D0 because it's always going to be there for trees. So how can we use symmetric group to define equivalence classes? Oh, sorry. First equivalence classes of trees, and then we'll see where the symmetric group comes into place for barcodes. So two trees are equivalent if they have the same barcode. So if their TMDs are equal. And a small remark, the TMD is not injective. I think that's pretty obvious, but typically this tree and if they have the same height, this tree have exactly the same barcode because the heights are the same. And well, they're different trees. So the question that we're going to be interested about in a moment is, can we find a map that takes a strict barcode and returns a set of trees such that two trees in the set have the same barcode, so are equivalent? So to reformulate, how many trees are there for a given barcodes?
Adélie, can I just interrupt? Because I'm not sure everyone here has seen this. So why are the two merge trees that you just drew not the same, so not isomorphic?
Because, well, they're not equivalent as combinatorial trees first. So
okay,
this branch here, for a combinatorial tree, we're interested in the adjacency matrix. So this branch here is attached to the main one here, whereas the corresponding branch in this barcode, in this tree, so it will correspond to the same bar in the barcode, but it's attached to the other branch.
Right.
Is that
yeah.
clear for everyone?
So I guess there is like a graph morphism, but the graph morphism would would change the height on that longest, on the trunk. Like it would send the trunk on the left to the branch on the right.
Yeah, it's a little bit complicated when you go into these morphism. Something I'm trying to figure out with another colleague, and it's a little bit tricky when you take the matching.
Yep. Yeah. But I guess that was just like one thing, is that as merge trees, these are going to be different because you had to like change the length on one of those edges in order to map one to the other.
Yeah, but I mean, just as combinatorial trees, they're different, so they cannot be the same merge tree either.
Right. Yeah. No, good point. And sorry, so the equivalence class on trees, so you're saying that two trees are equivalent if they have the same barcode, or?
Yeah, but it's not going to be very important. It was
okay. So this is like
for
a
this
candidate
overview of the question, but we won't really talk about this. This equivalence class anymore. It's just for this, to formulate this question in a really mathematical setting.
Okay, cool. All right, thank you. Apologies for the interruption.
Just to double check real fast, the longest is the reason why these trees aren't equivalent is because you're changing, like if you were to do that graph morphism, you've already specified because of the strict, like which component of the tree is the longest living one, and you'd be changing that here.
Yeah, so if you, yeah, I think what Justin and you said is correct, but for me, the easiest thing is really to see that, yeah. Yeah, I think both of you are correct in what you're saying. I mean, for me, it's just easier to think of combinatorial trees, but yes.
Okay,
Yeah.
sorry. Yeah, I didn't mean to slow you down.
No worries.
Yeah, I guess just to follow up on that. So like if the adjacency matrix is computed using, some of the kind of God-given labels based on heights, then that's going to like change because that B0, which corresponds to the highest leaf node in your drawing, ends up going to the second highest leaf node in the other one in order to do the graph.
Yeah, exactly.
All right, cool. All right, so I think we're all on the same page. Sorry for the detour.
No worries. So now equivalence classes on barcodes, which are going to be important for later. If two straight barcodes B and B prime, we can say that they're equivalent if they have the same death order with respect to the birth order. So without loss of generality, we ordered by birth times before, so we forget about the birth time, but technically you can define that with even without this ordering, right? You can just, we're basically looking at characterizing a barcode by the permutation that sends the ith birth to the jth death. Mathematically it can be written as this, but really what it's doing is looking the ith birth in the bar. We check which what order has the death. I think it will be easier with an example. So here, for instance, it's the same barcode as before. They're ordered by birth time. And again, we forget about this B0, D0 because it's always going to be there. So we just look at what happens to 1 to n. And here, the first birth here, because it's ordered as B1, and we look at its death, and it's the second death here. So it's 1 sent to 2. The second birth is sent to the third death, so 2 sent to 3. And the third birth is sent to the first death, so 3 sent to 1. And that's the permutation associated to this barcode. And because we're really interested in the image of these permutations to represent the death order, I'm always going to denote the permutations by their image instead of the maybe more common cycle notations. So here, this permutation will be denoted by 2, 3, 1. Is this clear for everyone? How we can associate a permutation of the symmetric group to a barcode? Cool. So this is a summary of what we've seen so far and a little bit more information. So if we have a merge tree using the elder rule, we can compute its barcode here from the merge tree to the barcode, and we can take these equivalence relations classes given by permutation, and we obtain what we can call a combinatorial barcode, which is just a permutation. So here, for instance, is 1 sent to 2 and 2 sent to 1, because again, 1 here is sent to 2 and 2 is sent to 1, and we forget about the main branch. But we can also look at combinatorial merge trees in a way that this diagram commutes. So a combinatorial merge tree is a combinatorial tree T with an ordered labels on the leaves, which would call the birth labels because it's what it corresponds to. So here 1, 2, and the 0. This is the one inherited by the height function that I was talking about earlier. And then an order on the internal nodes, which we'll call the death label because it's what it corresponds to again. But we just want this order to respect the ancestor relation, again, like no parent born before their children. And with this definition, this diagram commutes. So it's a really nice combinatorial point of view of this, what will be an inverse problem of looking at how many trees have the same barcodes, because basically everything can be made combinatorial in the sense that we don't need to know a barcode to know how many trees have this barcode. We just need to know the corresponding permutation. So this is now we're interested in inverse problems. So we have the TMD or persistent homology to go from trees to barcodes. And can we go back? How many do we have? Because we've seen it's non-injective. And can we characterize this combinatorially? The answer is yes. And I'm going to talk about first another inverse problem, which is called the TNS, and which is more biologically relevant because it's to build artificial neurons. So these 2 points are coming later. But yeah. So these are the 2 types of inverses we're interested about today. So there's first the stochastic inverse, which is the TNS. It's not a real inverse in the sense that it doesn't really, if you start with a barcode, build a tree, and then compute the barcode, or start with a tree, barcode, tree, you're not going to end up with exactly the same tree or barcode. But it's interesting because, again, there's a little bit of stochasticity added to this so that you can generate artificial neurons. And I'm going to show you that it's stable in a way. And then I'm going to talk about the real inverse in the sense that we're really going to see how many trees have the same barcodes and how this number of trees, so the tree realization number, can actually be used for statistics. So this is a little bit of an overview of this TNS. If we start with the barcode, obtain a tree, so using the TNS and compute the barcode, you can see that the 2 barcodes, it's not, sorry, I hope you can see it on your screen, but 2 barcodes are not exactly the same. And similarly, if you start with a tree, compute its barcode, and then generate a new tree with a TNS, you're going to end up with something that looks roughly the same, but not exactly. And this is used by LIDA and the Blue Brain project, for those who know about it, to generate artificial neurons. So how does the TNS work? I'm going to talk about mostly the mathematical part and not the neuroscience part, so you can forget about most of the diameter and size of neurons and stuff. But basically, the idea is to grow the tree backwards from the barcode. So you have your barcode and you basically have the time going this way, and you start growing your tree as every time you reach a birth, you basically get a new branch and so on. Except that you add a little bit of a stochastic aspect, as I was saying. So you add an exponential random variable to decide when you start growing this branch instead of starting it exactly at the value of the birth and death of the barcode. So the reference for this is this paper here. It's Lida and Catherine and other collaborators of the Blue Brain. So I'm just explaining what they did here. Yeah, so sorry, if you haven't seen, the exponential random variable is here. So just to
Adélie, do you always bifurcate off the trunk?
No, not necessarily.
Okay.
I'm going to give you an example here. So you start with the root R, and you start growing your tree in this direction here. So the time. Again, you should first define the tree and then embed it in R3, but I'm skipping those steps here. So you start growing your tree, and when you're reaching this point here, you should technically bifurcate, create a new branch. But because of this exponential, so the real value should be here, but because of this exponential random variable, maybe I will bifurcate a little bit before. So I'm starting to grow this, and then the trunk continues as well. Basically, I'm going to draw the trunk, the full one. It's supposed to end here, so this value. But again, because of the exponential random variable, maybe it will start a little bit, end a little bit before. So real value is a little bit before. And here as well. And the same thing here. So this branch, I can continue. It should end up here, but in the end, it's going to end up here. And I'm reaching another, sorry for the colors, they don't make sense anymore. I'm reaching another value here, instead of being a little bit further, I start growing my branch, which is supposed to finish here, but maybe it will finish a little bit before. And then I'm reaching the last one here. And this one, as you can see, because of the elder rule, so I'm going to come back to this later. If it's not clear, don't worry. It has actually three possibilities to attach, because it could be attached either to the main trunk or to the two other branches. So here I decide at random, and because Justin asked if it's supposed to be always on the trunk, I'm going to say no this time. So maybe today it's going to be attached here. So it starts growing, and again, it finishes here instead of here. So I basically grew, and I think with this, it matches the colors. So we basically grew a new tree from this barcode, and it's not exactly, if we compute the barcode of this tree now, it's not going to be exactly the same. The values are going to be the blue version here, and they will depend on this parameter lambda in the exponential random variable. Is this process clear? Cool. So this process of the TNS is stable in a sense that if I start with the barcode B, I generate a tree T, and then I compute its barcode B prime, then the bottleneck distance between these two barcodes are the probability that this bottleneck distance is larger than epsilon is bounded by this function, which you can see here depending on lambda. So basically, if lambda is very small, so the pink one here, you have no control over this bottleneck distance. So the tree can be completely crazy, and the barcodes will not be the same at all. If you take a very small lambda, so the black one, you have a lot of control. The barcodes are going to be almost the same. And all the work in the Blue Brain project for LIDA and everything is to tune this parameter. Actually, a good choice of parameter is lambda equals 1, where you have a little bit of freedom, but not too much. And with that, she showed that you get pretty good artificial neurons from biological barcodes, meaning barcodes computed from neurons. And just to show you, so we have first a lower bound, and only if the barcodes are equivalent in the sense that they have the same permutation. If you don't have this, then this lemma becomes insanely crazy to prove. So we only did it for this case, but it seems to work in general because, again, this is the blue curve here, and the distributions here are the real one, and the red dots are the experimental, and you see that they seem to be the same. So it should be inequality, and this might not even hold, but for the theoretical result, that's what we have. So again, all of this is super interesting because you can generate artificial neurons from barcodes coming from neurons. And now I'm going to talk about the other inverse, where we actually get the real set of trees. Again, that's not very interesting for applications in neurons, because the idea is to generate artificial neurons. If you get exactly the same tree, well, you haven't really gone so far. So if you start with a barcode, here we can see all the trees coming from barcodes with 3+1 trunk bars. If I take this example here, I will show you how we can construct all the trees with this barcode. So I start with the trunk, the black bar here, and then I can add the blue. I need to add the blue one, in the same way that I needed to add branches one by one for the TNS, except that here we forget about the stochastic aspect. So we forget about this exponential random variable. So the blue one can only attach to the black one, because otherwise it would break the elder rule. The red one here, on the other hand, it can attach to both the blue and the black one because it's included in them. And the purple one can attach to the blue and the black one, but not to the red one, because it would break the elder rule. If you have something like this, well, if you look at the height function, technically this would be the main bar, and then you would have this one. So it would break the elder rule because of this. I hope that makes sense. So this is the set of trees that realize this barcode. And you can do this for any, for all the barcodes. And again, this only depends on the order of the death with respect to the birth. So you can index that by the symmetric group. This is why we have 6 set of trees here, one for each copy, one for each permutation of the symmetric group on 3 element S3. So 6, which is 3 factorial. So the tree realization number of a barcode is the product of the indices of the bars, where the index of a bar is the number of bars it's included in. This we observed with Lida and Catherine, and then we later realized that Justin had also seen the same thing independently. But again, you can see this here for all the barcodes indexed by the permutation type here. This is basically the same thing classified, except that you don't see this as the recursive construction anymore. Something that I prefer to show is this one. Again, now it's indexed by the calligraph of S3, so you really see what's going on with the symmetric group. Here we have the identity barcodes. The identity barcode will always look like, if I forget about the main branch, something like this, where 1 sent to 1, 2 sent to 2, 3 sent to 3. And an interesting barcode is the one where we have this, which I will call the Russian doll barcode, because all the bars are included. This is the one with the most, the largest number of trees, which is always going to be n factorial, because the smallest bar has n possibilities to attach, the second one n-1, and so on. So you always get n factorial for this Russian doll, and always 1 for the identity. Are there any questions so far on this? Okay, good. Now, why were we observed this about the symmetric group, and then we started thinking whether it was useful for neurons or not. And it's interesting because the symmetric group, the classification, basically gives you only one. So you start with a barcode, which is kind of a lot of information and a little bit hard to do statistics with. And then you can end up with only a permutation type. And does this make sense or not? Can we get information from this? And the answer is, seems like it. Because here we can see biological barcodes. So again, coming from neurons. This is the bifurcation order. This is the termination order. And we can see that it's mostly located around the diagonal, meaning that barcodes coming from neurons have typically almost the identity barcode 1 sent to 1, 2 sent to 2. Again, the opposite barcode would be the other diagonal here, which would correspond to the 1 sent to n, 2 sent to n-1, and so on. So the Russian doll barcode. And I don't know, for me, it kind of makes sense. If you ask someone to draw a neuron for you, they would draw something like this and not something like this, right? So it kind of makes sense that you're close to the identity, but it's nice to see this on this plot. One plot that I really want to show, and that's actually the one that started the collaboration with Justin, Brendan, and Jordan, is this one, where we look at the logarithm of the tree realization number with respect to the number of bars with respect to the log of the tree realization number for different types of barcodes. First, the maximal one is the maximal tree realization number. We've seen it's n factorial, so log of n factorial is the black curve here. Then for biological trees, so real neurons compute their barcodes, this gives you the orange curve here. For bio-randomized, it's just you take the barcodes coming from neurons and you shuffle the values around and get a new barcode. That's the red curve. And then randomized, you pick a birth time and then you pick a death time larger than the birth time, and that gives you the curve. And it's very interesting to see that with only one number, so the tree realization number of the barcode, you're able to see that neurons are not random, right? Like they're very different from, oops, sorry. They're very different from those random blue barcodes. And later on with Justin, Brendan, Jordan, Lida, and Catherine, did I cite everyone? Yes. We identified this blue curve as this formula here, but I'm not going to go into details. So a summary of what we have so far. So we have the space of trees, this distribution. So this is the same as my motivation earlier. And we project that down to the space of barcodes, and we can classify barcodes using the symmetric group. And we can even project that further using the tree realization number to end up in Z and have like a nice way to do statistics, because obviously comparing things in Z instead of in barcode space, tree space, or anything, it's much easier. It's exactly what we've done in the previous slide. Now, what I'm going to talk about is how we can go further in this decomposition, and yet a much finer decomposition than the one given by the symmetric group. So to give you the motivation for this, this is a plot, again, the calligraph of S4 with all the barcodes. And if you take the identity, there are several barcodes with the identity. I mean, obviously, sorry. This one, for instance, has the identity barcode. I'm forgetting about the main branch now. And this one as well. But they're very different barcodes if you're planning to do statistics, or if you're doing any type of statistics, so landscapes, bend curves, whatever, average length or anything, they will be different for these two barcodes. But these two barcodes and many others are all in the identity permutation class. Same thing for the Russian doll barcode. There are several barcodes with the Russian doll that have the Russian doll, that look like the Russian doll. So the question is, can we make this finer and still keep the symmetric group classification, because it seemed to be useful in some applications? And the answer is yes. And the motivation for this, for me, is really, if you take, for example, these two barcodes, they, and you imagine you want to sort of walk on the edge between them. Basically, you're slowly switching to death times. So the middle point, I'm going to draw. So the first bar and second bar don't change, but the third and fourth one, they switch. So basically, in the middle, they will have the same value. Does that make sense for everyone? That's kind of intuition, right? Like it's not very defined here. But that's the idea of what's coming next, is how can we make this calligraph sort of a continuous version of this? And it turns out that you can do this, and it gives new coordinates on the space of barcodes, which is really nice. One last thing I want to say about this slide, the tree realization number here is in purple, the little values next to each permutation. And you can see that it has several combinatorial properties, including one, it respects the Brück order. So if you don't know what the Brück order is, you can just think of it as the shortest path between permutation and the identity on the calligraph. So for example, this one here, okay, let me take this one, is smaller than this one in the Brück order because it's closer to the identity. And you can see that the tree realization number respects this Brück order. So if you take a path between the identity and the furthest away barcode here, the tree realization number increases, but in different ways. And again, this like shows that there are a lot of connections between barcodes with this permutation classification and combinatorial and geometric group theory objects. And that's what I'm going to explain now. So this is one way to see the calligraph. And here's another. You can embed the calligraph of Sn on an n-2 sphere. Don't believe me for the indices. Here, S4 and a 2 sphere, so yes. So this is again the same Cayley graph, but just embedded on here a 2 sphere, a real sphere. And as I was saying earlier, if you want to walk on the edge, we're kind of switching to depth, but again, we have several barcodes for each vertex, so we kind of have a discretized version, and we would like a sort of continuous version. And you can achieve that by taking the dual and something that I will explain in a minute. So in black here, you see also the permutohedron, which is this Cayley graph here. And then we're going to consider its dual, which is called the Coxeter complex, which you can see in light gray behind. And I will show you this version in 2 slides. But let me maybe start with the 3-dimensional case instead of the 4-dimensional, because we can see what's happening. So basically, we're going to take first a birth and death separately. So now we're assuming either birth or death, whichever. So we have 3 birth or 3 death. So we are in R3. So R3 here generated by E1, E2, E3. And we're going to give new coordinates to R3. The first coordinate will be the one on this red line here, which is spanned by the vector 1, 1, 1. So that's the red line. If we project this, if we project x1, x2, x3 on this line, we're going to end up with the average of x1, x2, x3. Actually, it's going to come up later. And before I go to the projection so if I have a vector on this line, I can consider, I hope you can also see me on my screen, the perpendicular plane V, which is here shown in green. And we're going to look at what happens when we take the projection of a vector x1, x2, x3 in V. So we have one coordinate in the red line, and then 2 other coordinates in the red, in the orthogonal space here, V. And before that, I just want you to think of the hyperplanes x1 equals to x2, x2, x3, and x3, x1. Here in orange, blue, and purple. So here they're really planes. And when you project them to V, they become lines. And so if I have a point in R3 here, I'm going to get 1 coordinates on the red line and 2 coordinates in this space V. V, you could give it either normal Cartesian coordinates, or another common one to use is spherical coordinate, which is what we're going to do here. So you have a radius r, and then you have an angular coordinate, which gives you the position of V, for instance. But we're going to forget about this angular coordinates, and we're just going to keep the information of the order of the coordinates x1, x2, x3, which are going to be the position with respect to this hyperplanes. So for example, for V here, we're on the right of this orange hyperplane. So we have x1 larger than x2. We're below the blue line, so we have x2 smaller than x3. And we're on the right of the purple hyperplane, so x1 larger than x3. Believe me that if you get all these equations right, you end up with x2 smaller than x3 smaller than x1. I hope I'm not wrong, which gives you the permutation 2, 3, 1. So again, if I start with my vector x here, I have 1 coordinate given by the projection to the red line, and then 2 coordinates, the radius coordinate r, and then this angular coordinates v. But instead of keeping the angular coordinates, I'm going to forget about it and just consider the permutation associated to it. So basically, these hyperplane will decompose your sphere here, the circle, into n factorial because of the symmetric group parts. And each of these correspond to a permutation. And yes, we're losing information because there are several angles with the same permutation, but we're not going to lose so much information because, again, for large n, we have n factorial of these parts. So if we divide by n factorial, it's rather small. So here we have 6 of them, these 6 arcs. And yeah, so instead of the angle, we're just keeping the permutation. Is this clear for everyone? So here's the S4 version of the same thing. I can't do the 4-dimensional space. So here we leave already in this V subspace. So the green one, that was a plane before, and now we're in R3. So we already have one coordinate projected on this red line. And now we're looking at what happens on the 2-sphere. And these are the hyperplane xi equals xj here. And again, this subdivides the sphere into, I mean, we have a triangulation of the sphere where each triangle is indexed by a permutation. So here we would technically have 2 angular coordinates and 1 radius, and we keep the radius, but we forget about the angular coordinates and we just keep the permutation. This is exactly the Coxeter complex. So the light gray here, it's this object. So as you can see, for a vertex here, which corresponds to a permutation here, we actually, so this one, which is this one, you end up with a face of a triangle of the sphere instead. And because we have the radius of the sphere as well, technically, for one permutation, we have sort of a cone over this triangle. And we have this last coordinate, which I can't draw because I can't draw 4D, unfortunately, which is this red line. So to summarize all of this, we can get new coordinates on the space of barcodes by using, so this, I already told you that the projection to the red line is the average. So you have average of birth, average of death. And what's super nice is that the radius of the sphere is actually the variance of birth and death, so of the xi. So we obtain average and variance quite naturally. And then we had 2 permutations because we had 2 copies of this, one for the birth and one for the death. But technically, you can combine them into one because we're only interested in the death order with respect to the birth order. So you can see this as a sort of change of basis or whatever, but you can definitely compute this permutation and that will summarize your barcode. So barcode is almost characterized by average of birth, average of death, variance of birth, variance of death, and this permutation that we already used. And I showed you in this talk how to use it. The almost is because we lose these angular coordinates, but we really don't lose that much information. I mean, if we only consider the permutation, as I was explaining earlier with the 2 identity barcodes, these 2, we do lose a lot of information. But when you add the average and variance, you lose much less information. So this for now is only theoretical. I've done baby examples to see if it's a good way to use these as statistics, but I don't really have applications of this new decomposition yet. So a summary of what I've talked about today. We're trying to understand the relation between the spaces of trees and barcodes and how stable are, sorry, new coordinates with respect to, yeah, so the adding and removing bars is something we're trying to work on. There are several ways to do this. And yeah, if you want to add a bar in a stable way, technically you would need this bar to have the average to, the new bar has to be the average of the birth, comma, the average of the death. But this is really not nice and stable in the common the more common used barcodes stability. So I mean, yes, it's not very nice with respect to the more commonly used stability, but it's really nice with respect to this inverse problem and combinatorial point of view. And something we're trying to do with Justin and Brendan is to extend this to the space of trees, because we've realized that there are a lot of, I don't want to say inconsistencies, but it's sort of what's happening, right? If you start moving in the space of trees and moving in the space of barcodes, it doesn't really work that well. And there's like discontinuities happening. So my hope is that by using this, we might be able to solve some of these problems. So it might be another, we're not that much interested in stability here. We're more interested in seeing what happens, and maybe it would be a sort of a new stability. And to give you more of my intuition on this problem, but I'm not really, this is pure intuition. I feel like the symmetric group is tracking the generators. So again, if you have everybody look at me and not my screen, sorry. If you have two trees, one tree like this, and you slowly switch the two tips of the branches, technically you're doing a very continuous move, right, in the space of trees. But if you're changing generators, so if I have this tree here with this one a little bit higher, and this tree here, you haven't done a big change, but you changed generators. So the main branch, or the essential class, basically is not the same anymore. So I'm hoping that we'll be able to like catch a little bit more of what's happening with the generators using these tools. I hope that answers your question-ish. Okay.
Good. Actually, Adélie, before you wrap, can or maybe wrap up and I'll ask my question. So is this your last slide?
Before the last, yeah, but
okay.
Yeah, it's just a summary. So yeah, we've seen that. So we're trying to combinatorially characterize this relation to build also a new statistical tool. So maybe we can use this average birth, variance, birth, death, and permutation as a finer statistical tool than the trivialization number. And my hope as well, also a little bit related to what you were asking earlier, is, so for now, what the Blue Brain does with this TNS is take a neuron, compute its barcodes, and then generate artificial trees that look like the neuron you started with. But my question is, can you actually start from a artificial barcode? Can you build artificial barcodes that look like neurons? And because neurons have these specific type of barcodes in terms of permutation, basically we're trying to generate barcodes that have certain types of permutations. So actually that was more this point, trying to generate artificial neurons from artificial barcodes. It's already done for barcodes, but not for artificial barcodes. And again, as I was trying to explain earlier, trying to see if we can get new statistical tools or try to pull them from one space to another, so trees and barcodes. And all of this, I'm going a little bit backwards, sorry, by understanding this relation between spaces of trees and of barcodes from this combinatorics and geometry group theory point of view. So yeah, I'm done. So thank you to all of you for listening, and to my collaborators, and because I have this nice slide with questions.
I love it. Let's give Adélie a quick round of applause before doing more questions. Let me open the floor to have other people ask questions first, and if people need to work up courage, I can then ask a question. Does anyone have a question for Adélie?
I just have a quick question. So at some point in slide 20 or 19, you mentioned that you can generate neurons from barcodes, and you mentioned that with lambda equals 1, it generates quite good neurons. And I was wondering in what sense that is a good neuron. So is there any good criteria for that?
Yeah. So I'm not an expert in that because I'm not a neuroscientist, and because I didn't work directly with the TNS as a tool to generate neurons, but I worked more on the stability aspect. But I think they have properties of neurons. So actually, something I didn't mention at the beginning in the classification of neurons, neuroscientists were not really agreeing whether two different classes of neurons were the same or actually different. And the tools that they have to decide differences between barcodes are things like angles between the branches or thickness or things like that. And it was not enough to differentiate those two classes, but barcodes were. So that's how Lida started with the TMD, so persistent homology. It really helped to distinguish two different types of neurons. So to answer your question, to decide whether it's a good neuron or not, I think she used probably neuroscience tools and barcodes. So yeah, that's all I can say.
Thank you. Thank you for a great talk.
Thank you for the question, Woojin. Other questions for Adélie? And I guess maybe just as a quick follow-up to Woojin's talk, Adélie, I remember there being plots where it was like dendrites and then some other type of neuron, and you would like do the trivialization number curve. And you got like very different curves for those two.
Yeah, I prefer this one because it's both. I think it's both in the same one, but yes, there are different. So you can do this plot for different types of neurons, and you get different type of permutations as well. But this is one plot instead of two, so I use this one. But yes, you're right. You can. But again, I'm not an expert in neurons, so if anyone has questions on the more neuroscience aspect, maybe email Lida.
So maybe somewhat related to Michael's question in the chat. So obviously some of these symmetric groups you can like put inside of each other. Can we look at your Coxeter complex and see where like the Coxeter complex of S3 kind of fits inside of, or
you have
can fit
several
inside of?
Yeah, you have several copies of them of S. I mean, well, you have 6 copies of S3 in S4, I think. Am I wrong?
Yeah, well, I guess there's sort of a couple clear, like 4 clear ones where you could like maybe like permute the last few factors and fix the first one and kind of do that kind of insertion.
Yeah. I don't remember if you have 4 or 6. So I just got back from holidays, so my brain is a little bit getting back in business. But yes, you can see these copies of SN in SN+1, and depending which copy you're looking at in the inclusion, you will get different inclusions of barcodes. So yes, that's definitely related to the previous questions as well, of how this embedding works. This is something we're still trying to figure out because there are several ways to embed them, and what does that mean? And I'm trying also to see what that would mean in terms of trees, because we're doing all that for barcodes, but does this Coxeter complex thing make sense in terms of trees as well? And it seems to partially make sense and partially not make sense with merge trees, but with label merge trees from the discussion with Brandon. So we're kind of still trying to figure that out.
Yeah, and I guess maybe to get at Michael's question, like conceivably you could project onto these like representations of like S3 sitting inside of S4, and maybe quantify how far that projection is. Okay, cool. Yeah. Well, Woojin's leaving, and I think we should probably wrap up by 12 sharp. So Are there any last questions? People who need to step off are welcome to. But if people want to hang out and chat more, maybe Adélie has a few more minutes.
I can stay a few minutes, yeah.
Okay, great. Other questions for Adélie, if there are any? All right, well, if there's not, I'm going to go ahead and stop recording.